Welcome back to TalkTensors, everybody. Today we're going to be doing a really fascinating deep dive
Yeah, this is a cool one.
into the world of robots.
Human-robot interaction.
Yeah, right.
Yeah.
So how do we get these machines to actually work with us in a way that feels more natural?
Yes, and especially when they encounter objects that they've never seen before, right? Because that's one of the big challenges.
Yeah, I mean, how many times have you seen a robot video where it's like, oh, it can pick up this very specific thing, but then anything outside of that, it's like, I don't know what that is.
Right. Yeah, it's very limited. Exactly.
So this paper that we're looking at today, it's called NVP-HRI. Stands for Natural Voice and Posture-Based Human-Robot Interaction.
It's a mouthful.
It is a mouthful, but I think it really captures the essence of what they're trying to do. It's like, can we just talk to a robot and point and have it understand what we're trying to get it to do?
Exactly. That's the dream, right? To make it as intuitive as possible.
So before we sort of get into all the nitty-gritty details, what's the fundamental problem that they're trying to solve here in the field of HRI, human-robot interaction?
So traditionally, right, getting robots to work with humans has been a bit clunky, to say the least. Like you said, a lot of these systems require you to learn a very specific robot language.
Right, like programming or,
Yeah, programming or a set of predefined commands or gestures.
Right, like you have to do the robot dance.
Exactly. And you have to remember all these gestures. And then on top of that, in a lot of cases, the robot has to be trained on every single object that it might possibly encounter.
Right, which is a ridiculous amount of data and time.
It's just not scalable at all. And so this NVP-HRI system is really trying to address that.
So NVP-HRI is trying to get us away from this kind of rigid, pre-programmed way of interacting with robots.
Exactly. They're trying to move towards something much more intuitive. And the core idea here is surprisingly simple, but very powerful. They're combining natural voice commands, just like you would talk to a person.
Right, like, hey, robot, go get that thing.
Exactly, with pointing gestures, right? Because we do that all the time with humans.
All the time.
So they're bringing those two things together to guide the robot's actions.
So it's almost like, I'm imagining a parent teaching their child, you point to something, you're like, pick that up.
That's a great analogy. Yeah, that's very similar to what they're trying to achieve here.
That's kind of cool. So what makes this, really innovative, though, is this concept of zero-shot capability.
Yes.
And I think that's the really mind-blowing part. So can you unpack that a little bit? What does zero-shot mean in this context?
Sure. So zero-shot basically means that the system can understand and interact with objects that it's never specifically been trained on before.
So I can walk into a room, there's a robot, and there's some crazy gadget that I just invented, and I can just be like, robot, pick that up, and it would figure it out.
That's exactly the idea. It doesn't need to have a pre-existing database of millions of objects and know exactly what that object is. It can generalize based on your command and your pointing gesture.
So it doesn't need to know it's a flux capacitor or whatever.
It doesn't. Exactly. It just needs to know that's the thing that you're interested in and that you want me to pick it up.
Exactly.
Okay, so that's a pretty big deal.
Yeah, this is a huge leap from how we've traditionally thought about programming robots.
Okay, so from a machine learning perspective, how do they pull this off?
So, like any good magic trick, there's some really clever technology behind it.
It's not real magic, right?
Not real magic, but it feels like it.
Yeah.
So they're leveraging the power of some really cutting-edge machine learning models. And one of the key players here is the segment anything model, or SAM.
SAM. And SAM is, it's this incredible model that's really good at visually identifying and separating objects in an image. So it's essentially drawing a digital outline around anything it sees, regardless of whether it knows what that object is.
So it's basically doing segmentation. It's these are all the different pieces of the image that represent distinct objects.
Exactly. And it can do this even for objects it's never seen before.
So I could show it a picture of a Martian landscape with weird alien plants.
Yeah.
And it'd be okay, these are all the different objects in this image.
Exactly. And that's really powerful because it gives the robot a way to understand the visual world without needing pre-existing knowledge.
So SAM is providing the the visual intelligence to the robot.
Exactly. It's the eyes of the robot in a way.
But then there's the brain part. So how does the robot actually process this information and then take action based on what you're saying and where you're pointing?
That's where the other big player comes in, which is the large language model, or LLM.
So this is where like the GPT-3s and all that stuff comes in.
Exactly. So they're using a very powerful LLM, in this case, GPT-4. And this LLM acts like the brain of the system.
So the LLM is getting like the visual information from Sam, it's getting the voice command, and it's getting like the spatial information of where you're pointing.
All of that is fed into the LLM, and then the LLM can do some pretty amazing things with that information.
Oh, it can understand like, okay, this person wants me to pick up this particular object.
Exactly. It can understand the context of the request, the pickup, the move, the place, and it can use that understanding to then plan a sequence of actions that the robot can take.
So the LLM is basically like the reasoning engine that figures out how to translate your intent into like robot movements.
Exactly. And to make sure that the LLM stays on track and it doesn't sort of go off on a tangent and do something unexpected or potentially dangerous.
Which with LLMs, you never know.
Right. They can be a little unpredictable.
So to keep it on track, they've implemented something called essential control syntax.
Yes.
So what is that?
So essentially, it's a way of structuring the input that you give to the LLM. So the voice commands, the pointing information, all of that is structured in a very specific way.
So it's like giving the LLM a set of like rules to follow so it doesn't get too creative.
Exactly. It's like giving it guardrails to make sure it stays on the right path.
Okay, so we've got Sam handling the vision, we've got the LLM doing the reasoning and the planning, and then it actually sends commands to the robot to like move its arms and grab things.
Exactly. And the paper mentions a really impressive improvement in terms of how efficiently humans can interact with the robot using this system.
Yeah, they were saying like up to a 59.2% improvement in efficiency compared to older methods.
Which is huge if you think about it.
That's massive.
Yeah, because if you're trying to get a robot to do something and it takes, twice as long as it would take a human to do it, it's just not practical.
Nobody wants to wait around for a robot to like figure out how to pick up a cup.
Exactly.
So this speed improvement is a really big deal. And they actually have like a video demonstration of this, right?
They do, yeah. And it's really cool to see it in action because you can really get a feel for how intuitive and natural the interaction is.
And they made their code and the design open source, which is fantastic.
Which is great. Yeah, it's a great contribution to the research community.
Yeah, I mean, that's how we push this field forward, right?
Yeah.
Is by sharing our knowledge and letting other people build on it.
Absolutely. Collaboration is key.
Okay, so this is really cool stuff. But to really appreciate the impact of this research, I think it's helpful to take a step back and look at the history of human-robot interaction. Like, what are some of the things that have been tried in the past? And what were some of the limitations that this new system is trying to address?
Yeah, that's a great point. So, if we go back in time a bit, early HRI systems really relied on explicit programming. So essentially, you would have to program every single interaction, every single movement, every single object that the robot might encounter.
Yeah, it's almost like writing a script for every possible scenario.
Exactly. And you can imagine how incredibly time-consuming and inflexible that was.
Yeah, and if the robot encountered something that wasn't in the script, it would just be like, I don't know what to do.
Exactly. It would just freeze.
So then machine learning started to come into the picture.
Right. As machine learning started to develop, we saw a shift towards these more data-driven approaches.
So instead of explicitly programming everything, you would try to teach the robot by showing it a bunch of examples.
Exactly. And so one of the, the common approaches that emerged was to train robots to recognize specific objects using computer vision.
So like you would show it 1,000 pictures of a banana and it would learn to recognize a banana.
Yes.
But the problem is if you show it an apple, it would be like, what is that? I've never seen that before.
Exactly. And that's one of the limitations that we talked about earlier. These systems are only as good as the data that they're trained on.
Right. So it's not really intelligence. It's just like pattern matching.
It's sophisticated pattern matching, but yeah, it's not true understanding.
So what about like other interaction methods? Like, we've seen things like gesture-based interfaces.
Right. So gesture-based interfaces were kind of the next wave. And the idea there was to, use hand movements and body language, which was how we naturally communicate with each other.
To try to like make it more intuitive.
Exactly. And for simple commands, it can work quite well. Like, you could point to something and say, pick that up, and the robot can understand that.
But I imagine it gets pretty complicated when you start getting into like more nuanced actions.
Exactly. As soon as you start getting into more complex tasks, it becomes really cumbersome because you have to remember all these specific gestures and you have to perform them perfectly.
And not everybody is like a master of like robotic sign language.
Exactly. And especially for people with, physical limitations, it might be very difficult or even impossible to perform some of these gestures.
So you're kind of trading one form of rigidity for another.
Exactly. You're moving away from the rigidity of the programming, but you're introducing this new rigidity of the gestures.
So then what about just using natural language, like just talking to the robot?
Right. So natural language processing has come a long way. And, now we have these systems that can understand human speech pretty well.
Well, language can be ambiguous.
Very much so. And especially in an environment where you have a lot of different objects.
Like if you say, pick up the blue thing, and there's 5 blue things in the room.
Exactly. The robot's going to be like, well, which one?
And it might just pick up the wrong thing.
Exactly. And that can be very frustrating.
So all these limitations, the reliance on pre-trained object recognition, the complexity of gesture control, the ambiguity of language, this is kind of the backdrop against which NVP-HRI emerges.
Right. It's addressing all of these shortcomings.
So let's dive a little bit deeper into how it actually works, like under the hood. So what are the steps involved in this whole process?
So the first step is for the robot to build what they call a structural object representation of its environment.
So it's basically trying to create like a mental model of the world around it.
Exactly. And it does that by using the depth data from its camera along with the segmentation information that it gets from SAM.
So Sam says these are the different objects.
And then the depth data tells it where those objects are in 3D space.
So it knows how far away they are, and it can kind of like build a 3D model of them.
Exactly. And from this 3D model, it can extract important structural information like the size, the shape, the position of each object.
So even if it doesn't know what the object is, it has some basic understanding of its physical properties.
Precisely.
Okay, so now the robot has this like spatial awareness of its surroundings.
Right. So the next step is to figure out what the human wants to do with these objects.
Enter the human.
Enter the human. And this is where the voice command and the pointing gesture come in.
And it's processing both of those simultaneously, right?
Yes, it's doing this in parallel. So on the one hand, it's analyzing the spoken command and it's trying to extract the intended action.
Like pick up, move, put down.
Exactly. And it's also trying to extract any specific details about how to perform the action. So for example, if you say, pick up the cup carefully, it needs to understand that carefully means it needs to be gentle.
So it needs to adjust its grip strength accordingly.
Exactly.
And for this speech-to-text conversion, they're using the VOSK API.
Yes. And they chose VOSK specifically because it's very accurate and efficient. And it can also handle speaker identification, which is important if you have multiple people giving commands.
Right, because you don't want the robot to get confused about who it's supposed to be listening to.
Exactly. So while that's happening, it's also analyzing the pointing gesture.
So it's using the RGBD camera to see where your arm is pointing.
Right. And by combining that pointing direction with the 3D structural representation of the objects, it can figure out which object you're most likely referring to.
So it's basically doing like a line of sight calculation. It's like, okay, this person is pointing in this direction. Which object is closest to that line?
Exactly. And that's how it identifies the target object.
So it's almost like the voice command is giving the general instruction, and then the pointing is acting like a laser pointer, saying, this is the one I want you to do it to.
That's a great way to think about it. Yeah, it's giving that spatial grounding to the language.
Okay, so now we've got the action, we've got the target object. What happens next?
So now comes the really crucial step, which is integrating all of this information and actually generating the robot's actions. And this is where they leverage the power of GPT-4.
Our friend, the LLM.
Exactly. So the LLM gets all of this information, the processed voice command, the structural information about the target object, and it has to come up with a plan.
So it's like, okay, this human wants me to pick up this thing that's shaped like this and located over there. How do I do that?
Exactly. And to do that, it needs to think about the robot's own capabilities, its kinematics, its limitations, and it needs to come up with a sequence of movements that will achieve the desired goal.
So it's not just about like reaching out and grabbing the object. It's about like planning the whole trajectory of the robot's arm.
Exactly. And to make sure that GPT-4 generates a sensible and safe plan, they use a technique called prompt engineering.
Which is basically about giving the LLM very specific instructions and examples to follow.
Right. It's like giving it a set of guidelines to make sure it stays on track.
So it's like, these are the kinds of actions you're allowed to do. These are the limits of your movement. Don't go outside of these boundaries.
Exactly. And to further enhance safety, they've implemented a really clever cross-checking mechanism.
So it's not just trusting the LLM blindly.
Right. Before the robot actually executes any movements, the planned trajectory is checked against a model of the environment.
So it's like, okay, if I move my arm along this path, am I going to bump into anything?
Exactly. And if it detects a potential collision, it can actually provide feedback to GPT-4.
So it's like, hey, GPT-4, your plan's no good. I'm going to hit that vase if I do that.
And GPT-4 can then revise its plan to avoid the obstacle.
So it's like a feedback loop between the robot's perception of the world and the LLM's planning.
Exactly. It's a closed loop system, which is really important for ensuring safety.
And this seems to have a pretty significant impact on the robot's ability to avoid collisions.
Yeah, they found that the success rate for generating collision-free trajectories went up from 73% to 94% with this cross-check mechanism.
Which is a huge improvement.
Yeah, it makes a big difference.
So to kind of summarize the whole interaction flow, it's like the human gives a voice command, points to the target, maybe specifies some details like speed or orientation, and then before the robot does anything, it kind of shows you what it's planning to do, and you have to confirm that you're happy with that plan.
Exactly. And that confirmation step is really important because it gives the human that final level of control.
Right, because you don't want the robot to just go rogue and start doing its own thing.
Exactly.
Okay, so they put the system to the test, right?
Oh, yeah. They did a lot of really thorough experiments to evaluate how well it works in practice.
And they weren't just like testing it in a lab, right? They actually took it out into the real world.
Right. They tested it in like kitchen and living room scenarios with all the complexities and clutter that you find in those environments.
And how did it do?
It did remarkably well. It was able to successfully interact with a wide range of everyday objects that traditional object recognition systems often failed to even detect.
That's impressive.
It is. And, they also did some lab experiments where they specifically compared NVP-HRI to other existing methods.
So they were comparing it to things like pure gesture-based control, natural language processing alone, and those vision language models.
Exactly. They wanted to see how NVP-HRI stacked up against the state of the art.
And what did they find?
So they found that NVP-HRI was significantly more efficient in terms of task completion time, like we mentioned before, up to 59.2% faster than gesture-based control.
Which is a huge advantage in terms of usability.
It is. And what's really interesting is that they found that the age of the user had a much smaller impact on the interaction time with NVP-HRI compared to the other methods.
So it's more intuitive for a wider range of people.
Exactly. Which is really important if we're thinking about robots being used in, assistive contexts, like helping older adults or people with disabilities.
Because you don't want a system that only works well for like young, tech-savvy people.
Right. You want something that's accessible to everyone.
And what about accuracy? Like, how good is it at actually identifying the right object and performing the correct action, especially with these novel objects?
So they did a really clever experiment where they had participants interact with a bunch of identical, previously unseen objects.
Like they just went to a hardware store and bought like a dozen random things.
Exactly. And they found that NVP-HRI was very accurate even with these unknown objects. It was able to correctly identify the target object based on the pointing gesture and execute the requested action.
So it's not just fast, it's also accurate.
Exactly. And they found that providing visual feedback to the user, like showing on a screen what the robot had identified as the target object, further improved accuracy.
So it's like the robot is showing you, okay, this is what I think you want me to pick up. Is that
Exactly. And that visual confirmation helps to prevent errors.
And it's not just about lab experiments, right?
Yeah.
They also looked at user experience more broadly.
Right. They did a big online survey with over 390 participants, and they asked them about their preferences for different HRI methods.
So real people, not just like researchers in a lab.
Exactly. A diverse group of people. And the results were really clear. The overwhelming majority of participants strongly preferred NVP-HRI.
So it's not just like a theoretical idea. It's something that people actually find intuitive and enjoyable to use.
Exactly. And they said that the main reasons for their preference were that NVP-HRI was simple, it was easy to understand, and it was efficient.
Which are all really important factors if we're talking about robots being used in everyday life.
Absolutely.
Okay, so this is a really exciting development in the field of HRI, but now I want to shift gears a little bit and move into our novel notions segment.
Okay, I'm excited.
So thinking about this research, what are some of the future directions, the new avenues for exploration that this work sparks for you?
So this paper immediately makes me think about, how can we extend this multimodal interaction approach to understand even more nuanced human intent?
So we're going beyond just the basic commands?
Right. What if we could incorporate more subtle cues from human posture or facial expressions to allow the robot to understand the user's emotional state?
So if someone's pointing hesitantly, the robot might be able to pick up on that and be like, okay, this person's not really sure what they want me to do. Maybe I should offer some more guidance.
Exactly. Or, if someone's clearly frustrated, the robot could try to adapt its behavior accordingly.
That's really interesting. So it's not just about understanding the what and the how of the command. It's also about understanding the why and the emotional context.
Exactly. It's about making robots more empathetic and responsive to human needs.
That's a really cool direction. And what about the other side of the equation? How can the robot provide more intuitive feedback to the human?
Right. So currently, the system relies on a GUI, a graphical user interface, for confirmation.
So it's basically showing you a picture of what it's planning to do.
Exactly. But what if we could develop more embodied forms of feedback?
So instead of just showing you on a screen, it could actually use its own body language to communicate.
Exactly. What if it could use its gaze direction or subtle head movements or even nonverbal sounds to convey its understanding?
So if it understood your command perfectly, it might nod its head, or if it was confused, it might tilt its head and make a questioning sound.
Exactly. It's about using these nonverbal cues to create a more natural and intuitive communication channel.
So it's almost like we're trying to blur the lines between how we interact with other humans and how we interact with robots.
Exactly. We want to make that interaction as seamless and natural as possible.
And NVP-HRI seems like a really promising step in that direction.
It definitely lays the groundwork for some really exciting possibilities.
Well, I'm excited to see where this research goes next. For our listeners who are interested in diving deeper into the technical details of this work, we'll have a link to the research paper in the show notes. Thanks for joining us for this deep dive into the world of human-robot interaction. And until next time, keep on learning.